webinar or be in a room with somebody who is. You must attend for 60 minutes. If you're in a room with others, the number of people not logged in must be provided by the person who is, and you can send the names to that email address listed there. If you did not request a credit at registration, please email the email address there again for that request and respond to the registration confirmation email. Again, we can't offer the certificates of completion for watching the webinar recordings, although we're trying to work out a way we can do that, and hopefully by next month we'll have that in place, but we'll see. So one of the things is, as the presenters are presenting, you'll find a question box in the drop-down dialog box that you have. If you have questions for the speakers, please type them in, and type them in as soon as you have them. And at the end of both speakers, we'll be able to answer those questions, but we'll answer them after both speakers have talked. Also, if you missed the poll and there's greater than one person in your room, please, in the question box, list down the number of people that are in your room. It helps us document how many people are listening to the webinar and helps us show how important it is. If you have any comments about what you find useful for the webinar and how valuable it is, please include that in the question box too. We'd be glad to have that information in terms of documenting, again, how valuable the webinar series is. You can find a copy of the slides in the handout box in the dialogue area of the, find it in the handout box. And so, Michelle?
Yeah, sorry to interrupt. We are having a little bit of difficulty uploading the handouts. We will get that loaded as soon as we can. In the meantime, the handouts will be emailed.
Okay, very good. Thank you, Michelle. So with our first speaker, we'll go right into it. Our first speaker is Darren Lytle of the U.S. EPA. Darren works for the Water Supply Water Resources Division, where he joined in 1991. Dr. Lytle's primary goal has been to research drinking water quality, where he has investigated and published many works on drinking water systems, particularly on distribution system corrosion control and water quality, filtration, biological water treatment, and iron and arsenic removal. So, Dr. Lytle, I'll hand the floor to you.
All right, thank you, Tom. So, just to start out, you can see the title of my slide has changed from the original title. The original title had conventional water treatment, and I can tell you right now up front that conventional treatment does not remove strontium, so we're not going to talk about that, but rather we'll talk about ion exchange and lime softening approaches. And I want to start out by, of course, acknowledging my co-investigators, Hannah Chait, Dan Williams, Miley Pham, and Christy Mullen. Let's see here. Get this.
Okay.
Hold on a second. There we go. Okay, start out with my EPA disclaimer. So just a little bit about strontium and its elemental properties. It's a naturally occurring alkaline earth metal, and most importantly, it behaves like calcium chemically. So certainly we can think of the treatment approaches that we use for calcium removal are probably going to be effective for strontium removal. It does have a number of manufacturing usages, including alloys, fireworks, ceramics, glass. It's used to block X-ray emissions from cathode ray tubes. In terms of where it's found naturally, it's found and widely distributed through the Earth's crust and the ocean. In fact, if you see surface waters along the oceans, you'll find elevated levels of strontium that are in some of those waters impacted by the ocean waters. Majority of compounds are soluble. Strontium compounds are soluble, and the main exposure routes are through drinking water and various foods. Why we're concerned about it from a health respect and standpoint, and admittedly there's limited studies, but there is indication that it affects the development of bones, basically by replacing calcium in the bone structure, creating skeletal abnormalities, rickets in particular, and certainly again, as I said, it substitutes calcium in the bone. So that's our main issue with regards to health effects. why we're looking at it. In terms of regulatory relevance and where it stands, as we've looked at it, it's been on the contaminant candidate list 3, as well as the unregulated contaminant monitoring rule 3, and under the unregulated contaminant monitoring rule, a non-cancer health reference level of 1,500 micrograms per liter has been established, or 1.5 milligrams per liter. In 2014, late 2014, the agency came out with a preliminary regulatory determination on strontium. In other words, the agency is going to take a serious look at the potential benefits and possibility of regulating strontium. As we stand today, the final regulatory determination has been delayed to consider additional data that includes health risk benefit analysis, health effects data, and treatment data and cost analysis. So that's where we're at with the rule. So the agency is still looking at it and still considering it, which makes, again, this presentation relevant. So where is strontium? And I was somewhat surprised that, so we did some analysis just looking at USGS's database and US EPA's storage databases, and plotted up concentration of strontium across the country, and you can see that the various concentrations, as we get darker in color, represent higher and higher concentrations. And so if we take that 1.5 to 2.5 milligram per liter concentration, a lot of waters, a lot of groundwaters, these are groundwaters, a lot of groundwaters across the United States have elevated levels. Of particular interest and concern with regards to high levels is right up the road from us here in Cincinnati, and that's up north of Dayton, Ohio, between Dayton, Toledo, and Columbus is the biggest and most concentrated area of high strontium concentrations, in the United States. And as we move, you're going to see that all of our field studies are systems that come from this area of the country. When it comes to treatment, when we first started looking at this, as it turns out, there really wasn't and hasn't been a lot of information on the treatment of strontium from drinking waters. There's some information on industrial wastewater, looking at, folks have looked at absorption and ion exchange and biological treatment. And then there's been also some publications on radioactive isotope removal of strontium-90, which has been regulated. So if you look at the literature, there's information on absorption technologies, nanofiltration, and biological water treatment as well. But in terms of specifically looking at drinking water and some of the drinking water, more historic drinking water approaches, not really a lot of information. So with that said, and that little bit of background for you, what I hope to do here in the rest of my time is to provide you a kind of an overview of some of our past bench scale research that we've performed looking at the impact of lime softening on strontium removal. This is work that one of our past master students, Alyssa O'Donnell, had performed, and I'm just going to show you a couple slides of some key highlights from that data. And then I'm going to go into looking at data that we've collected over the past year and a half or so, a full-scale drinking water treatment studies that have used lime softening or ion exchange softening to remove strontium. And of course, those systems, their goal wasn't to remove strontium. In fact, I don't think that they really even knew necessarily what the concentration of strontium was in their waters, but they're removing hardness ions, and that was the goal of their treatment. Just real briefly and quickly, the lime softening jar test that we performed, and we did a lot of these, but I'm just going to highlight a few of them, where we took 3 different groundwaters from again, this section of Ohio up the road from us here in Cincinnati that had concentrations natural strontium between 4.2 and 21.8 milligrams per liter. Again, these are hard waters here in Ohio. We performed jar tests on these waters, as well as we spiked groundwaters with strontium to give us different concentrations of strontium. And we also performed jar tests with laboratory waters. And we use these jar tests to examine the impact of pH, calcium concentration, strontium concentration, and dissolved inorganic carbon concentration on strontium removal. Able to do these, of course, with jar tests in a controlled environment on a laboratory bench really helps us understand the mechanisms for removal. And then further, we took the precipitated solids and we did solid and surface analysis on those to try to understand, what is the mechanism of strontium removal. This is just a picture of the jar test that we performed, and again, We also did conventional treatment or alum and ferric chloride coagulation experiments, and I can tell you up front, without going any further, that the best we could remove was maybe 5 to 10% reduction at best under a variety of conditions. So coagulation is not an approach to remove strontium. But again, I want to highlight just a couple of situations here, a couple of jar test results that are going to be pretty important, and I think kind of help us understand some limits maybe and the relationship between water chemistry and strontium removal. And this is just one of the jar tests from a private well, actually fairly close to us in Cincinnati. The source water had 4.2 milligrams per liter of strontium in it, 127 milligrams per liter of calcium in it. And so we increased the pH of this water basically, by adding lime and appropriate amounts of soda ash as well, and we plotted pH on the x-axis versus strontium concentration on the y. And again, this water starting at 4.2 milligrams per liter, and what we see is as we increase the pH by adding more and more lime, we see that the strontium level drops off. The final strontium level drops off to a minimum of just under 1 milligram per liter at about pH 10.5. So it shows this strong effect of pH and with regards to impacting its removal. And then I've also plotted on the other graph the pH versus the percent removal. And all this is showing is, again, that percent removal is increasing as we increase our pH up to about 80% in this particular water. I also plotted, my line moved. We were reformatting the slide backgrounds, but this line, this red line here is supposed to be the 1.5 milligram per liter reference dose. But the point here is that health reference dose. And the point here, though, is that we can meet that in this particular water under optimized, we'll say, conditions. The next graph, though, shows a water with a lot more strontium in it. This is a water up the road north of Dayton, and it has 10.9 milligrams per liter of strontium and 112 milligrams per liter of calcium. We ran this test twice, did 2 separate jar tests, and again, the same kind of trend is that we saw as we increase our pH, add more lime, we get better and better final strontium, or lower and lower final strontium numbers until about pH 10, 10.5, somewhere thereabouts, and then strontium levels start to increase, suggesting perhaps a point of minimum solubility maybe at that pH. Again, my dash line, the 1.5 milligram per liter reference line, is moved, but it should be down here. And I guess the point I want to mention with this particular situation is that even though, as a percentage-wise, we're getting 80% or so removal, that's the best we can get, and we're not able to get to the 1.5 in this particular water under what I'll call, optimized conditions with regard to pH anyway. So there does seem to be a limit. We took all the jar tests that we performed using our natural waters. So there was another water that we used. We did multiple jar tests, and we put it all together, site 1, 2, and 3. And we plotted up the calcium removal versus the strontium removal. And this is just a key take-home message that we saw in these jar tests, was that whatever percent removal of calcium we got the same percentage removal of strontium. So they were pretty closely linked in terms of their removal and their removal effectiveness, indicating that they're being removed together in some fashion, maybe perhaps co-precipitation or some other mechanism. And lastly, what I want to show you is we did some experiments where we took the same water, a water that only had 0.417 milligrams per liter of strontium in it, and we spiked it at various dosages, all the way up to 10 milligrams per liter. And we did our jar test at what I'll call an optimized pH and an optimized. This should not be. This is the initial, but the optimized pH for softening, which I believe was about 9.5. For all these conditions, and we looked at what the final removal was. So if we look at the percent removal on a percent removal basis, what we found was that for calcium, pretty much across the board, we got a similar percent removal of the calcium, independent of what the strontium dose was. But and the same thing goes with the magnesium, but more importantly, the strontium, as we found basically we got the same percent removal approximately across the whole initial strontium concentration range. But the more interesting thing that becomes really clear is that if you plot up the initial strontium concentration versus the final strontium concentration, there was a really nice linear relationship. In other words, whatever the initial was, you could predict what the final was going to be based upon that linear relationship that we saw. So I guess the take-home message here is that is that the final concentration is really being dictated by what the initial concentration was, and again, there's if you're trying to shoot for a target level, it suggests that perhaps there's a limit to which you can reach with regards to strontium removal, depending on what that initial concentration is by lime softening. Okay, so went through that real quick, but let's go to the full-scale treatment plants. And again, as I said, in Ohio here, we're fortunate to, or maybe unfortunate, to be the hotbed for strontium. And so this is just another closer look at Ohio and these test waters that we work with, and then more importantly, the full-scale plants, 8 full-scale plants, 4 ion exchange plants, 4 lime softening plants that we went to in Ohio. We monitored for over a year, sent bottles out to them. The operator sent the bottles back, taking treatment samples through their treatment train, raw water, through each ion exchange softener, settled water, through lime softening, and then filtered water. And so again, a lot of strontium in these waters. These are the waters. Again, 8, I'm all over the place. 8 systems here. The first 4 are ion exchange systems, and the last 4 are lime softening systems. So just taking a look at the initial strontium concentration in the ion exchange systems, we're ranging from 13.3 to 27.3, so well above 1.5. You can see the calcium concentrations, the magnesium concentrations, and total hardness. And for the lime softening plants, we had lower concentrations as a whole. We had a 1.1 up to a 15 milligram per liter plant that was using lime softening to reduce hardness, and again, getting some, as we'll see, strontium removal along with that. So let's start by taking a quick look at the ion exchange plants. This is just a picture of the 3 of the 4 that we visited. We visited different sizes, different size plants. Most of them were pretty small systems. And let's just jump right in looking at some of the results of this test. So in this particular system, this is what we call Site 2. The influent water has upwards of 13 to 15 milligrams per liter of strontium in it. If we look at the water coming out of each softener, with the exception of this particular day around March, where softener 2 had some high peaks, and as did all the softeners in April, the strontium concentrations coming out of the softeners were quite low. Most cases near 0 or near the detection limit. But if we look at the finished water, the final water, the blending of the 3 softened finished waters together, along with, as we all most know, ion exchange plants typically will blend back or blend back a certain fraction of the water back to their water, around the softeners and back to their water. And so as a result of the blending practice at this particular plant, the final strontium concentrations were between 3 and 4 milligrams per liter. Just looking at things on a percent removal basis, with the exception of, again, that time period between March and April, we're talking about, about 75% removal of strontium. But again, the softeners themselves are approaching 100% removal. It's the blending. It's the blending ratio that they use that gives the final concentration, or dictates the final concentration. Another plant has had 18.7 milligrams per liter of strontium. Site 3, again, same kind of thing. We have a raw water. We have a water going onto the softeners, which are basically the same waters. Through each softener, in this case they have 2 softeners, through each individual softener, levels were generally quite low. But again, as a result of blending water back, their final strontium concentration, was again in this particular plant, between 3 and 4 or so milligrams per liter. And again, we're looking at it on a percent removal basis over here. But again, that's dictated again by the recycle, the amount that they bypass. And then lastly, Site 4, again, a similar situation. This has 27 milligrams per liter of strontium in it, but the same thing. High concentrations in the raw and filter influent. There's a filter in advance of the softeners in this particular plant. Again, each softener is very effective at removing strontium. And again, in this particular plant, they're around 5 or so milligrams per liter because they're recycling, or they're bypassing about 20% of the water around the softeners and blending it back later. Okay, let's jump to lime softening. Here's just pictures of the clarifiers for, in one case, a filter, in the case of Site 6, of 3 of the 4 sites that we visited. And in the case of softening, we'll start out with Site 5. In the case of lime softening, this had about 2.7 milligrams per liter of strontium in it, 58 milligrams per liter of calcium, and 22 of magnesium. And we'll start out by looking at the strontium concentration through the treatment train. So in this case, I had 2 sources, two wells. In the case of the red and black, the green, it represents after aeration, so they have an aeration system in lime. Blue is prior to filtration, and then the pink is the final or finished water. And so what we see here is, again, these concentrations of about 3 or so, 2.7, 2.8 milligrams of strontium to start in the 2 sources, and after aeration that remains the same. Prior to filtration and the finished water, both are about the same. So by the time we get through and the water's approaching the filters, most of the strontium has settled out, and there's really not much being taken out by the filters at all in this particular plant. And the final concentrations are around just over 1.5, 1.6 or so milligrams per liter are the final concentrations coming out of this plant consistently over the course of the 1-year evaluation period. If we put this on the other graph in terms of percent removal, what we find is that calcium removal is between 60 and 70% pretty consistently removal, and strontium removal is just below that at about 50 to 60% removal, and then the magnesium falls off at about 20%. Next plant that we visited, Site 6, that we monitored over a course of a year, started out, they had a source water about 15 milligrams per liter of strontium in the black. Again, after flocculation and settling, the concentration, and then following filter and finished water, the concentrations of strontium were all about the same. So really not much difference. So most of the strontium is precipitated out before it even gets to the filters in this particular plant. The final concentrations of strontium are between 3 and 5 milligrams per liter typically. And if we look at this in terms of percent removal, what we find is that we're roughly around 70 to 80% removal of both strontium and calcium. So it's very, very close for both. And then lastly is a plant that has 3.5 milligrams per liter of strontium. This is a lime softening plant that, as you can see, they have a little more variability in their source water or their raw water in terms of strontium concentrations. But if we look at the finished water, the pre-filtered water, and it should be the reverse, but pre-filtered and the finished water, they're about the same. Very low concentrations of strontium, very effective removal of strontium in this particular plant. In terms of percent removal, we're talking between 80 and 90% removal of between 80 and 95% removal of strontium and calcium, very similar in terms of the percent removals. So that's a quick overview and running through some of the yearly monitoring that we went through in these plants. But let's sort of pull back now and just take a whole look at the whole all 8 plants and just sort of summarize what we observed. So so again, with the ion exchange plants, as I said, ion exchange softeners themselves, have operated properly, are very effective at removing strontium. They're going to get 90, 95, 100% removal basically of the strontium. And as it turns out, what dictates what final strontium concentration you have is how much you bypass. And so for those 4 plants, you can see over here we calculated the amount bypassed, based upon the raw water and the water going on in the softeners and then the water coming out of the softeners. And so the amount bypass percent is, in these plants between 20 and 30% or so. So, and that's really what's dictating the concentrations, again, of the final strontium concentrations. In this case, none of them are at 1.5, but these have very high concentrations to start. Could they get below 1.5? Yeah, but they would have to bypass a lot more, or a lot less, I should say, of their water around those softeners. Average percent concentration, again, although I put numbers on here, again, it's dictated by how much they bypass. Same thing goes with calcium and magnesium. Whereas in the case of the lime softening plants, we have a range of percent removals, anywhere from 50%, 49%, up to that one plant was 94% removal. And, we look at the initial concentrations and the final concentrations, and again, that 1.5 number is, might be a challenge to meet if your initial strontium concentration, if that number, is a number that we think about in terms of potential regulation, that number could be hard to meet for a plant that has a high concentration to start. But the others were consistently below that number, and again, the percent removals are here. I also thought I'd plot up just the percent removal of calcium and percent removal of strontium. I showed you in the jar test that there seemed to be this nice relationship. So we did. We plotted it up, but we did see a nice relationship, although it isn't this one-to-one relationship that we observed in the jar test, but rather it's, I don't have a linear regression plot here, but you can envision and see that there seems to be a pretty decent line, going between all four of these sites, calcium removal percent versus strontium. So there does seem to be some relationship between the two. I didn't mention it earlier, but when it does come to mechanisms of removal, we are interested in trying to understand that, and we have spent some time looking at the residuals, the sludges. We did so in the jar test. We spent a lot of time trying to look at what is there. Is strontium carbonate, for example, precipitating out? And we in fact didn't find that. We found that calcium carbonate was precipitating out with strontium presumably mixed in the matrix of the calcium carbonate and actually impacting it mineralogically. So we don't fully, we need to do a little more work there to try to understand exactly what's happening, but there is a lot of literature in the geochemical field on the relationship of and the impact of calcium on strontium on calcium carbonate precipitation. So we certainly need to do a little bit more to try to understand exactly what's happening here precipitation-wise, but nonetheless, I think it's going to be interesting work. So we're going to continue with that. If we look at the sludges, though, in the case of the two lime softening sludges that we did get some material from, Site 5 and Site 6, we find that that the strontium concentration as a weight percent is 0.64 and 2.72, and that's dictated by how much. Site 6 has more strontium in it, so it has a higher percentage by weight of strontium in the lime sludge. So I'll wrap it up. As I showed you, I think it was pretty clear that strontium from the map is relatively widely distributed in groundwaters across the United States. Here in Ohio, just north of us here in Cincinnati, we're lucky to have a lot, or not so lucky. Jar testing showed that strontium is effective at removing strontium, although there does seem to be a relationship between pH. I showed you that, calcium, and initial strontium concentration. Again, the final strontium concentration was related to what the initial concentration was. So the more you have, the more difficult it is to be for you to be able to get down to a low level. And then lastly, I demonstrated and showed you a lot of data on full-scale studies showing that lime softening and ion exchange softening do effectively reduce strontium concentration. But again, we need to think about that initial strontium concentrations being important. And then when it comes to ion exchange softening, the recycle ratio is going to be really control what you can get to, because the softeners themselves are very effective at taking strontium out. And lastly, acknowledge a couple folks, Steve Harmon and Keith Kelty, for water and solids analysis help, and of course all the folks from the water utilities who have been very, very kind to us and help us with this study. Thank you.
All right, thank you very much, Darren. We will take questions for Darren after the second speaker speaks, so please keep sending in your questions and we'll have them ready for Darren in a short bit. A little housekeeping. Also, if you missed the poll in the beginning or haven't sent it in yet, in the questions box, put in the number of people in your room if you have more than one person in your room. It helps us figure out how many people are tuning into the webinar. Also, unfortunately, and I apologize that the slides did not make it to the handout box in your dialog box, so I apologize for that, and we will email out the slides to all the registered people who are registered for the webinar, and we'll get those out today or tomorrow. So, with that, our next speaker is Eugene Liang, and if I can get the slides pulled up here, I will pull up his information. And what you're seeing is, there we go. So Eugene works for the California State Water Resources Control Board of the Division of Drinking Water. He is a drinking water technical specialist and is based at the Richmond office in the San Francisco Bay Area. He has been with the drinking water program since 1997. He was a sanitary engineer and associate sanitary engineer at the Santa Clara District through 2010 and was responsible for the oversight, inspection, and permitting of water systems and treatment facilities. He now provides technical support to the division's district offices on treatment-related matters. He graduated from UCLA with BS and MS degrees in civil and environmental engineering. He is a registered civil engineer and a T4 water treatment operator in California. So with that, I'll hand the podium to Eugene.
Thank you very much. Can you guys hear me?
Yes, yes, we can.
Okay, great. Good afternoon, everybody. Thank you for giving me the opportunity to share with you California experience with the nitrate treatment technologies for drinking water. So my goal today, the presentation goals for today, is I want to highlight the latest treatment technologies that's being used in California for nitrate treatment. I want to bring some awareness to some of the key issues that must be addressed and considered in order to implement these technologies. How they differ from some of the existing traditional treatment technologies that we have already out there. A lot of these kind of optimization of existing technology will be the first part of my coverage. And then also we kind of provide an update of some of the project status for some of these projects that we have around the state. So the outline, first I'm going to touch on the nitrate MCL, the associated health risk, and the nitrate treatment options that we have available out there. And then the two key treatment technologies area that I'm going to cover today is the optimized ion exchange treatment and then also biological treatment. These appears to be the area that we have the most work on for nitrate treatment in California right now. And then we also will be touching on the point of use treatment devices as interim solutions. We do have a lot of individual homeowners that is having raw water from the private wells coming that's over the nitrate standard. So we do need some point of use interim solution for them, as well as for public water systems that have nitrate over the MCL. So first, here's a good picture that I found on the web from USGS indicating where in the United States that we have very high nitrogen input or fertilizer that's being used probably for agricultural area. So you can see from this map, there's a very good chunk of America that we have high nitrate. And then in California in particular, you can look at the Central Valley. That's where we have most of our agriculture going on, and that's the area that we have found the highest nitrate concentration in California. And looking at this map, which is focuses on the nitrate problem that we have in California, you can see that right here is around here is the Monterey Bay, where the north symbol is, and then right here, this valley is the Salinas Valley. So in that area, we have a very high nitrate concentration from a lot of the raw water. You can see based on the scale down here, having the red and then the darker red dots is over nitrate as milligram nitrate as NO3. So 45 is the drinking water standard if you have nitrate as nitrate, not as nitrate as nitrogen. So you can see that we have a very large chunk of wells here in the Salinas Valley that's over the nitrate standard, as well on the eastern portion of the Central Valley along Highway 99. If you're familiar with I-5 is on the western side of the valley that goes from San Francisco Bay Area down to Los Angeles, and then the eastern highway is Highway 99. And then you can see from this area we have a lot of sources that's over the nitrate drinking water standard. There's a really great report that's published on the issues with the nitrate problem that we have in California, and also a good summary of what the technical issues are, and you can find the report at the UC Davis report site, which the link is provided on the bottom of this slide. So touching on the nitrate maximum contaminant level, as with the rest of the country, the nitrate MCL is 10 milligrams per liter as nitrate as nitrogen, and then for nitrite, the MCL is 1. For nitrate, we consider it as an acute health risk, as you know, that has significant health effects by even ingesting water over the MCL for a short period of time. The vulnerable populations are infants below the age of 6, as well as pregnant women. And the big concern for there is because the nitrate being reduced to nitrite in the infant stomach can cause blue baby syndrome. can interfere with the oxygen carrying capacity in the blood, and the baby can potentially turn blue because of the lack of oxygen. So that's the vulnerable population for nitrate. So for the Division of Drinking Water for our program, we require systems that provide treatment for nitrate must make sure the treated water is meeting the drinking water standard at all times. So they need to really have good, robust treatment, and it's meeting the standard all the time.
Hey, Eugene?
Yes.
This is Tom. Sorry, we have a couple comments that you're hard to hear. Could you get a little closer to the mic, perhaps?
Is this any better?
Yeah, I think that's a little better. Thanks. Yeah.
Okay. All right. For the typical treatment target for people providing nitrate treatment, we recommend, and most of the proposals comes in will be the starting point will be at about 80% of the drinking water standard of the MCL as the starting point for treatment. For the online nitrate analyzer that's available these days, it really has allowed water system to blend and treat a lot more effectively. In the past, we only have grab samples or from using laboratory analyzed samples available, but online analyzers has really helped water system to optimize the treatment. However, these analyzers are quite expensive. It really requires a skilled technician to take care of them, and they cost around roughly $16,000 each. So the target for systems that can afford the online analyzers, after a good performance record, we allow them to actually move up closer to the MCL, but at all times we're below the MCL for the treated water. Treatment target of 80% can be typically achieved either by blending of the treated water with a bypass flow, or they're treating 100% of the water with some of the nitrate leaking through its treatment process. So either a combination of both of them for them to achieve the 80%. And you may ask, why don't we treat to a lower level? And it's strictly cost, because if you treat nitrate to any lower level, the cost goes up quite a bit, and water systems already have difficulty meeting the MCL at 80%. So here's a good diagram for nitrate treatment options. The best available technology that's identified in regulations for nitrate are ion exchange, reverse osmosis, and electrodialysis. Typically, what we have seen in California, we only have ion exchange is the primary treatment technology, and then there's also reverse osmosis on a point of use scale. There are very few systems that's using reverse osmosis on the full scale, probably due to the disposal issues of the concentrate for nitrate treatment. For most water systems, especially the smaller ones that have a nitrate problem, we go through the non-treatment options first. The non-treatment options including the well abandonment. If they can drill a new well that's below the nitrate MCL, we much prefer that because it really eliminates the long-term O&M. And if they can find any alternative sources or blending, if they can purchase water with lower nitrate concentration by a neighboring system and be able to blend it down, or construction pipe works to mix the water together to below the MCL, we encourage that. Now, if they have exhausted all of that, and including potential consolidation with nearby system, the only thing left we can do work with them is on the treatment options. So for treatment options, we have primarily, until now, we have worked on the left side of the columns for nitrate removal. So using either ion exchange or reverse osmosis, as I've mentioned, is the typical approach. For the ion exchange is the full-scale system, and for RO, most of them are point-of-use devices. Where electrodialysis, we really don't have, I think we only have one treatment plant in the state of California, and it's not for nitrate treatment. So we really have not had anyone then propose or do full-scale electrodialysis for nitrate treatment. And then on the right side for nitrate reduction, this is where there's a lot of work that's going on in California. We actually now have demonstration scale plants going on for nitrate treatment. We have 2 of them, which I'll cover later in this presentation. So I'm going to touch on the 2 topics. First, for the general background on ion exchange. As you know, ion exchange has been around for a long time. It's a proven technology. It's used successfully for nitrate, arsenic, and perchlorate removal. They use different types of resins based on the targeted contaminant. For technical considerations, there's when you install nitrate treatment, it's really important to you to remember the performance. When you have a virgin new resin, it's going to perform best, and then it really depends on the regeneration process. So as you regenerate, it may lose capacity over time, and it's really critical for you to regenerate it pretty well. Also for nitrate peaking is a concern, especially when you use a non-nitrate selective resin. As the exchange capacity for the ion exchange resin is filled up, if you use a non-nitrate selective resin, sulfate can potentially bump off nitrate and resulting in a nitrate spike. So it's really important if you're targeting nitrate treatment, you need to use a nitrate selective resin unless you have taken other precautions. Then there's also the regeneration method. There are systems out there that likes to do concurrent regeneration and then countercurrent. And then one of the key things to deal with is treatment residuals. You have a really high nitrate concentration and salts that you need to dispose of as you regenerate these ion exchange resin and what to do with it. And then also there's concern for disinfection byproducts as well. Some of the ion exchange resin, as you regenerate, if you hit from some of the resins, if you chlorinate, you actually may form some nitrosamine. So the basics, here's a diagram from ion exchange. If you're not familiar with it, it's actually very similar to a household softener, but you just use the different type of resin. When you're doing softening, you're using a cation ion exchange resin. When you're doing for nitrate treatment, you are using an anionic resin. That's the only difference. So in this case, as with typical, raw water will be coming in from the top of the ion exchange resin bed. It will go through. And in here, the chloride ion will be exchanging with the nitrate ion, which is both of them are negative. And so the water coming out with higher chloride concentration and the nitrates being absorbed, being exchanged onto the ion exchange resin. And during regeneration process, you use a very high strength sodium chloride solution, which is typical, so it's table salts. And then pretty much you knock off all the nitrate and sulfates from the resin, and then you end up having a lot of chloride available. And then you can put it back into service. And that's pretty much the basics for ion exchange. So the number one issue for dealing with ion exchange is brine disposal. So there are a few key innovations for brine volume reductions that have really helped ion exchange treatment. The first thing, as I've mentioned earlier, is the online analyzer. It's able to allow water system to operate closer to exhaustion for the column. So online analyzer-driven operations allows to regenerate only when the columns becomes exhausted. And then also improve in hydraulics. I think a lot of company has worked on the distributors for the ion exchange resin so that the water will pass through the actual column more like a plug flow. It's going through evenly, so it's able to improve the hydraulics. And some companies have actually spent significant research on how to regenerate and be able to segment, break out the different components of the waste brine. Some portions may only contain mostly sulfate and no nitrate, and that portion can actually be metered back into the treated water slowly. So the sulfate return is one of the inventions that have really innovations that have helped reduce the regenerant volume for disposal. And then last but not least, some of the regenerant is used more than once. So again, they can help in reducing the volume of brine that needs to be disposed of. So here are some pictures. Actually, I'm going to go over them a little quickly. Here's one of the companies that we have out there. This company is Ionic. They have actually put together skid-mounted treatment plants that they have out there, and as the combination of technology that they're using is they're using the optimized ion exchange treatment and be able to help with improve the regeneration process and able to reduce the brine volume that's being disposed of. And this is one of the projects we have going on in Central California. And definitely by having skid-mounted treatment plants, components, and they're allowed to have off-site assembly and minimize the engineering that's needed on site. So this is one of the companies out there that's working on this type of treatment. And for the ion exchange treatment cost, if you look at it, the key thing for treatment is the capital cost for the treatment plant. The O&M cost is the key here. It's the salt cost and brine disposal and O&M. These are the key portion of the cost that it's often that the water systems need to bear in the long run. Especially in our state, we have state revolving fund that's available to help water system with the capital cost. But the long-term O&M cost is the most important part that needs to be affordable. So looking at looking at the diagram here, it's estimated that as even for water just slightly over the drinking water standard, say at 12 milligrams per liter nitrate nitrogen, the cost for treatment is already at about $150 per acre foot. So the cost is quite significant, and then we have areas of California that is significantly financially disadvantaged, and this is one of the areas that we're tackling in California. So so it's pretty much a linear relationship. So as the incoming nitrate concentration increases, the salt cost and the brine disposal cost increase significantly, especially for inland systems. This brine disposal options may include evaporation ponds or ocean discharge after treatment. So when you, for example, if you're in the Central Valley, if you have nitrate treatment, you can either go to the evaporation ponds that they're located in the Central Valley itself, or maybe they need to haul it up to the San Francisco Bay or down into Los Angeles, where there's a wastewater treatment plant that can take the brine and have it treated prior to disposal into the ocean discharge. So for treatment performance and requirements and other considerations, one of the key things is for treatment plants, we need them to be consistently below the nitrate and nitrite MCL. For ion exchange, generally speaking, we request that they provide continuous disinfection after ion exchange. To ensure the treatment reliability, treated water nitrate must be monitored continuously. So with the availability of an online nitrate analyzer, that has really helped that. For operator certification in California, we classified that as a T2 treatment facility. So for ion exchange treatment, it is really, from our perspective, it's a mature technology, but it still may be too difficult for small water systems to operate on its own. A possible solution that we're trying to work on right now is for small system is technical consolidation of systems, where we will be having treatment plants at multiple locations that is operated remotely and monitored by the contract service operator, so that this is a technical consolidation because they are too far from other systems to physically connect. And we are also working on a proposal right now on a project that if we have multiple systems that's using the same technology at multiple sites, it may be possible to reduce the brine disposal cost as well. Because as it stands right now, for each of these sites, when they need to dispose of brine, they need to have a truck from the particular water system to take it to the brine disposal facility directly. But if they have the same similar brine characteristics and we can demonstrate the consistency of it, I think some of the brine receiving companies, they're willing to have the commingling of the brine, and that could be a big potential for saving on the disposal cost of brine. So we're working, currently have a project that we're working on to see if that proves successful. So now I'm going to switch gears to touch on nitrate treatment options. The other part that we have going on right now is biological denitrification. So biological denitrification of nitrate is nothing new in the wastewater side, but for drinking water, really have very limited experience with it. So the fundamentals for it to work is if you have raw water with high nitrates coming in, you need to provide electron donor. The electron donor of choice for the treatments that we have right now is acetic acid or vinegar. So the water would go through a biological reactor that is anoxic. So it's a nitrate in the biological reactor is able to reduce the nitrate into nitrogen gas. So it'll be harmless nitrogen gas that can be released into the atmosphere. And after the biological reactor, it will go through a post-treatment system to filter out the excess biomass that have been developed because in the bioreactor. So there's generally a filtration process. It's not surface water treatment rule, but we have a filtration process to take out the biomass, and then followed by disinfection to inactivate the biological activity that is present in the water, and then the water is sent into the system as treated water. And we have some filter waste from that. It's very similar to surface water, so that you can dewater the solids, and then potentially for the water to be recycled back to the head of the plant for treatment. So the nitrifying bacteria is the one that's doing the work, that's break down the nitrate to nitrogen gas, and the nitrifying bacteria is actually naturally present. We do not seed any of these treatment plants. It's actually for the bacteria that's naturally occurring. You're just encouraging their growth and providing them the biological reactor environments for them to grow. The key benefit of biological process is there's no concentrated waste stream to deal with because the nitrate has been reduced to nitrogen gas. So for the technology variations, we have actually 6 companies that's been working on, or cities that have been working on biological treatment. And the biological reactor design is the key variations from them. We have designs in fluidized bed that is upflow. We have fixed bed that's downflow. We have a continuous stir tank reactor type. So in this case, they have some crouton-sized foam that's being stirred around in a reactor where they have attached growth for the biofilm. We have some biocatalysts. This is the one case that the bacteria actually comes pre-populated inside some capsules so that there's no starting up process that's needed. Then there's also membrane biofilm reactor, and then there's also that's another one that the water goes through a membrane and tangentially flowing past the membrane surface for it, for the biofilm growth. The electron donor used, as I mentioned, is acetic acid, and then the nutrients that sometimes that's needed is phosphorus. Generally speaking, the bioreactors are not preceded and rely on naturally occurring indigenous bacteria. And we have single pass and multiple pass system. So I'm going to go through some of these slides rather quickly, but we can answer some questions. So for the reduction process, this is the upflow reactor sequence. You have groundwater coming in from the bottom. As it flows up the reactor, first it will take up all the oxygen for aerobic respiration, and then the next step is goes to denitrification, and then perchlorate reduction and sulfate reduction. So for nitrate treatment, and with the use of online analyzers, we target for the nitrate reduction to come to near completion. So that's the target. So there's a concern if you during extended off cycles that if you have water just sitting in the reactor, that it will consume all the nitrate and can go past that. So that's one of the concerns that we work with. So the key concerns for biological treatment is that the biological treatment is a living treatment process and prefers steady states. During the system startup or system upset, where can we send the off-spec water? So that's the key. What would be the source of drinking water for customers during startup and upsets? Because some of these are groundwater system that does not have a storage tank. And also during system upset, and if there's incomplete reduction, there could be concern for excess nitrite as well. So we really need to work it just right. And then in addition, for key concerns for biological treatment is how quickly can a system recover after there's a chemical or water flow interruption. Say a well broke down, so the system has become dewatered, or you have lost chemical feed. How quickly does it come back? And so there are a lot of site-specific testing that's required for us in order for us to permit water system to go through it. So right now we have one system that is demonstration scale for nitrate treatment. It's a fixed bed process. It's using the process so the water comes up from the well. It gets its electron donor for acetic acid and phosphoric acid for food. It goes through the bioreactor. It has intermediate degas stage, and then the polishing filter for turbidium removal using a polymer, and then it's being disinfected. So as you can see from a single pass, as the water goes down, here you can see that this dissolved oxygen level drops down to near zero. And then the next one is the black line here. You can see the nitrate will drop to zero. And then if you have perchlorate present, perchlorate will be the next to be removed. So for nitrate treatment, you will only be concerned about the blue line and the black line. So the demonstration that we have in California right now is at the city of Delano. It is in Central Valley. It's at the Well 35 facility. It has a 570 gallons per minute well. 200 gallons per minute is being treated, and 370 gallons per minute is being bypassed. It's a full-scale demonstration facility that's in service now. Right now, it actually came in service probably around 3 months ago. So the water is being served to the community, and we have been getting good results from it. That the biological process is working well, and they're actually on the way to allowing 24/7 operation without an operator on site. So we're working on that currently. So here's a picture of just some of the pictures of the chemicals, the metering pumps, and all the pipings. So the big blue vessels here is one of the bioreactors, and then the polishing filter is the same size on the other side. Other projects that we have going on in the States right now is the biocatalyst system. This is the one that has the pre-populated, the little beads this project is going on right now in Sunny Slope Water Company in Southern California. They're also using it for nitrate treatment. It is a vendor water system funded project, and it's a single pass system. So this system right now is going through testing. The water is not served to the public yet, but it should be coming real soon. So the other treatment that I've mentioned is we have the CSTR type project, and then also the membrane biofilm. And these two projects, they don't have any full-scale project right now, but they have gone through some demonstration scale work, and we have given them conditional acceptance. So for treatment performance requirements, I think the key part, again, similar for ion exchange, we just want to make sure the water is consistently below the nitrate and nitrite MCL. We want low turbidity for effective disinfection, and that the water is reoxygenated so that there is adequate DO, and there's no taste and odor problem. So for other considerations for biological treatment, the operator certification is important. It's more complex. It's a T3 facility in California. And one of the key challenges that we have in California is there's not many water operators, designers, or regulators that's familiar with the technology. So we're working on this. Hopefully we have more long-term treatment reliability, more data is available, and how well it works on intermittent operation. So we have quite a few projects going on, and we should be able to share our experience with you later when we get more on how they work. From our perspective, biological treatment is definitely an emerging group of technology in drinking water applications, but we definitely need more experience before it should go to the smaller system. So here's some cost estimates, but I think I'm out of time, so I'm going to skip over that. So here is a summary of the projects for biological that we have going on in California. We have one in West Valley Water District that's for biological for perchlorate treatment, the one that I've mentioned in Delano for nitrate. And then at West Valley, they're going to also build a parallel plant with fixed bed reactor that's coming on, as well as the project down in Sunny Slope for nitrates. And so for treatment options, the last one I just want to touch on is reverse osmosis. As I've mentioned at the beginning, we have a lot of small individual homes and maybe small systems that have nitrate problems that they're looking into long-term solutions, but they need an interim solution. Point of use RO that's certified under the NSF and C58 standards are very effective for nitrate treatment, especially if the nitrate concentration is below 2 times the MCL. If your source water is greater than 2 times the MCL, an adequate feed pressure is critical. So in that case, you may need to get the booster pump systems to improve the efficiency of the RO system for it to provide water that consistently is below the MCL. And so for the reverse RO-based POU, discharge consideration is sometimes a concern, especially for some of the local authority regulating discharges. But the key point here is when we're looking at the net increase in nitrate concentration when you have a point of use RO is very small, because there's a lot of bypass water that's not being treated and goes into the same septic system, so the net gain for nitrate is very minimal. So here's a nice summary table for the technology comparison. For the full-scale poly for biological process, I need to correct that there's actually 4 in progress right now. For ion exchange, we have multiple of them in California, and the RO point of use device, we have a lot of interim and small systems that's using this type of technology. And so the closing thoughts, there's no silver bullet for solving the nitrate problem. Probably a combination of different treatment technologies, regionalization and consolidation will be needed to solve this problem for California. Nitrate treatment technologies are complex to operate. The TMF, the technical, managerial, and financial capacities and O&M costs remains the major challenges for a lot of our small water system. And while we look for the long-term solution, interim solutions are also needed, as the above will require planning and coordination. So,
thank you for our speakers, Darren and Eugene, for excellent presentations today. And thank you for attending. We love doing these webinars, and I'm glad people are finding them valuable. Stay tuned for next month's webinar, which is March 28th on source water protection. We'd love to see you there.